Okay, good morning, everyone. So before we formally start, teaching the content, let's talk about how the course is evaluated, right? How it is taught. So the course is taught according to my natural language processing textbook. So I think our library has it. I didn't bring it, but it's called Natural Language Processing Machine Learning Approach. You can borrow one from the library, and if there are not enough copies, I can order more. But I think I'll try to make the slides self-containing, so you don't have to read all the contents from the book in order to understand it. All right. For teaching materials, there is another online course which I recorded. I recorded it over 2 years. I spent a lot of time recording it. So I put it onto Bilibili. So not me, Han Meng and Yulong, they put it onto Bilibili. So if you want to learn a Chinese version, if you didn't quite understand what I taught in the English class, you can look at Bilibili, right, to catch up. So how are you evaluated? So after each class, I will leave you some exercises. And you can do the exercise to gain scores, right? And I will also leave you some programming assignments. You can do those assignments to earn scores. So basically, I won't have a final exam. So everything is based on your own interest and your own time devoted to the course, right? So from my past year experiences, right, after chapter 1, chapter 2, right, a lot of students, they returned their homework and they gained quite some scores. But then as the course gradually move on, the difficulty increases and a lot of students, they stopped doing homework or programming. But I guess what's this goal? The goal is that if you pass, if you earn more than 60 scores in the end, I will basically give you B. If you earn maybe over 80 or 85, depending on how many students earn over 80, I will give you A. I don't have a bell-shaped score distribution. So for anyone, if you make efforts, if you show me that you catch up with the math content, you can earn an A. So that's the basic idea. I know that not everyone's research topic is natural language processing, but many of the content will end up useful for computer vision, for speech, etc., I guess. So learning this class will be useful to you. Okay. So take it easy. And the content is quite mathematical. All right. So it's quite mathematical. So what does it require? It requires linear algebra, of course. I guess most of you have learned it in undergrad courses. Calculus. You need calculus knowledge. And also you need functional analysis. If you know a little bit about functional analysis, it'll be useful. But if you don't know it, it'll be fine also. If you know probability theory, it'll be very useful. But if you don't know it, you can still take the class. Okay. Algorithm. If you know algorithm, it'll be very easy for you to understand things. If you don't know algorithm, you might have some difficulties somewhere. I think that's all. That's all. The prerequisites. You still have a chance, I think, to confirm your selection of the course, or get out of the course, right? So I try to make the evaluation very lenient. But the content is mathematics and algorithm heavy. Okay, it's not a learn NLP in 24 hours course. It's a real NLP course. Okay. Are questions here? Do you have questions about the logistics? Okay, so if no questions, let's start. There will be 16 weeks, but my book has 18 chapters. So what I normally do is that I remove the latent variable chapters. So chapters 12 and 18, but I keep all the rest of the chapters, okay? If you find that you struggle, okay, which chapters can you skip? I tell you, chapter 9, okay, you might skip chapter 9. Chapter 10 and chapter 11, these three, you might skip, okay? And those contents that are relevant to the 3 chapters in chapter 15, all right, part of chapter 15, you can skip. The rest, okay, if I say I removed the 2 latent variable chapters, right, leaving 16 chapters, that's 16 weeks. And then I further remove 3 chapters, okay, leaving only about 13 chapters, right? And further 1 chapter, part of a chapter. So it's a little bit more than 12 chapters. I think those you should be able to fully understand, okay? And chapter 1 is no-brainer. You don't have to think about it to learn this chapter, okay? So which means only about 11 chapters and a little bit more, okay? Throughout this term. That's it. Okay, we can start. Okay. Good morning, everyone. Welcome to the natural language processing class. So this term will consist of 16 chapters in which we discuss 16 different topics. So for today, we introduce chapter 1, which contains an outline of the course, as well as an introduction to natural language processing and its tasks. So first, let's look at the outline for today. I will discuss 3 main things. So the first is, what is natural language processing? Okay, an overview of the field. And then secondly, I will discuss tasks that are currently being solved in NLP. So I classify them into 4 categories as shown in the outline. I will go over them one by one. In the third part, I will talk about why do you want to learn NLP from a machine learning perspective? Why do you want to learn NLP by learning machine learning techniques? And then I'll give an outline of this course. So first of all, let's look at what is the field, what is natural language processing. Okay, so in the broadest sense, natural language processing refers to algorithms that automatically understand and generate human languages. There are no other languages in nature except for human languages. So natural language processing is also referred to human language technology. Okay. So such algorithms can range from a very simple string matching algorithm to a very complex check system. Okay. I guess when you learn algorithms and data structures, you learn algorithms that try to match 2 strings, right? To find the longest common substring. Okay. Those algorithms, if your input is natural language, can be regarded as NLP algorithms. The big commercial deployed systems such as ChatGPT are also natural language processing systems. Okay. These algorithms are very useful for your smart microphone, smart speaker, for your machine translation, for your internet search, etc. So those applications all contain NLP technologies. And for this course, after you learn this course, you learn the algorithms and mathematics principles behind NLP technology. So after you learn this course, we would expect that you will be able to understand the current cutting-edge technology. You'll be able to read NLP papers by yourself. You'll be able to not only make use of NLP tools, but also tweak them and deploy them according to your own need. Okay, so that's a goal. So NLP has been a very traditional field in AI and computer science, and there has been 3 main stages in its development. Okay, so first stage. So NLP research started at the dawn of computer science. Okay, at the very early age in 1950s, people start to think about how algorithms can help automatically translate one language to another. Okay, so at that time, the major technology are rule-based techniques. What do I mean by rule-based? So computer scientists, they hire linguists to write linguistic rules. For example, say verb follows subjects, right? And verb can be transitive, intransitive, ditransitive. It can have objects. Okay, so if I have a transitive verb, I find its subject, find its object, and I translate this, we call predicate argument structure into another language. So linguists write rules. I eat fish, translate to 我吃鱼, etc. between English and Chinese. But this kind of rule-based techniques has limitations because human languages are very, very ambiguous. When I say something, there could be different interpretations. So, for example, if I say they can fish, so can be a modal verb. Okay, they're able to fish, right? Or a can be a verb. They can fish means they put fish into cans, into containers. So such ambiguities are prevalent in languages, which makes it very difficult for a set of linguistic rules to cover all those behind languages. As a result, in the 1960s, there was a famous report to funding agencies in the U.S. Like showing this limitation. There was a famous example for machine translation from Russian to English. The original sentence means that the spirit is strong, but the flesh is weak. Okay. But because spirit and flesh are both polysemous words, they have many meanings. So the resulting translation was, the vodka was pretty good, but the meat is bad. Okay. So this kind of translation means that if you use a simple set of rules, your translation can deviate a lot from the original meaning. By that reason, rule-based method saw a downturn. So people lost interest, and the government cut fundings. So NLP research received less attention until the next stage, like in the late 1980s. So because of increase in computing power, so statistical algorithms became possible. So people built statistical models that learn from linguistically annotated corpora. So they ask linguists to do annotation to data. And then they use machine learning algorithms to learn, or to train a model. And they use statistical models to make disambiguation tasks. To decide, okay, the probability of translating the sentence into this sentence is higher, or to that sentence is higher. Okay. This kind of statistical models gradually showed their potentials for resolving ambiguities, and they became the dominant approach. Of course, work has shown that statistical models surpass rule-based method in different applications. Okay. And then later, the third stage, from mid like 2010s. So as the computing power continually increased, so deep learning models gradually took over simple statistical models as the dominant approach. So this model, right, they train a deep neural network rather than a shallow linear model. Okay, and basically they do similar things. They calculate probabilities of different outcomes, and they compare one output to another. Okay, nowadays, if you look at the dominant method, so they train deep neural networks, okay, over large data. And then they use sort of pre-training or self-supervised learning to gain model initial parameters, and then they fine-tune the model over small amounts of manually labeled data in order to achieve the competitive performance. So ChatGPT is such an example. And I believe many of you have tried it, and it has shown impressive capabilities. All right. So this is a brief history. As you can see, the whole history of modern NLP advances are driven by the increase of computing power and machine learning algorithms. Okay. So as you can foresee, computers become faster and memories become larger, and the deep neural networks will be deeper. Okay, there will be more data that are used to train the models, and the model performance will continue to increase. So next, let's look at what tasks are solved in NLP. Okay, so I classify them into 4 categories. So one I call fundamental natural language processing tasks. One I call information extraction tasks. One I call text generation tasks. And one I call other applications. Okay. So the first one, computational linguistics tasks, or fundamental NLP tasks. They are a branch of NLP that integrates linguistics and computer science. And they are, of course, a very traditionally resolved problem in natural language processing. Okay, so from the linguistic perspective, you have theoretical linguistics, corpus linguistics, right? Computational linguistics, different branches, right? Cognitive linguistics, etc., etc. So computational linguistics is a branch. They use this branch, okay, they use computational algorithms to automatically solve linguistics tasks. So what are the tasks? You have phonology, study the pronunciation, the sound. Morphology, to study words and how do you break words into small pieces. You have syntax, you study the composition of sentences. You have semantics, you study the meaning. Discourse, right? You study the structure of longer text. And pragmatics, right? How the purpose of using different languages. Okay. So let's look at them one by one. So word level syntactic tasks. So morphological analysis. So different languages, they reside in a large spectrum. Sitting on one end, there are morphological rich languages. So you use morphemes, right? So subwords to carry meanings. So such languages include so European languages such as German, Dutch, Czech, etc. Also Asian language, Arabic, etc. Okay, these are Arabic. These are like morphologically rich languages. On the other side of the spectrum sits morphologically poor languages. They use structure of sentences to denote meaning. Of course, you know Chinese is a morphologically poor language. And there are a few morphemes that you can think about. And English is actually another morphologically poor language. There's no rich morphology. But morphological analysis is to break like the morphemes, the subwords from sentences. Okay. So a second word-level syntactic task is word segmentation. So this is useful for Chinese, Japanese, and Thai. So because the sentences are written as sequences of characters, and you want to extract words from it, okay? Over a long history, words are very useful for NLP applications, such as information retrieval. So these are useful steps for the Chinese processing pipeline. Nowadays, because deep neural networks have strong representation power, word segmentations might or might not be necessary. So it's still under debate in the academia, while a large number of researchers believe word segmentation is not useful anymore. Tokenization. Tokenization is like a pre-processing step for English processing. So you have this prime S, for example, and you have some period tokens. If you say Mr. Smith, right? So this period is not a sentence ending punctuation. But if you say he built a house, period. So this period should be separated as a punctuation token. So tokenization is processing step to do this. And part of speech tagging, pause tagging, is another sentence level task. Okay, let's look at the next slide for part of speech tagging. So you have a sentence, and you already did pre-processing to turn them into words, to turn a sentence into words. And then you should assign each word a syntactic category. So this is called parts of speech. And we know from our grammar book that there are nouns, there are verbs, there are adjectives, etc. Okay? So the task is to use an algorithm to automatically assign a part of speech to each word. You see, this is simple, right? We just look up a dictionary and we get a part of speech. But as I mentioned to you earlier, for sentences like they can fish, right? So the words are ambiguous. You have to look at the context to better understand what kind of parts of speech each word has, right? So this requires machine learning algorithms to resolve ambiguities. Okay, so up one level, at the sentence level, syntactic tasks, they look at the sentence composition. And there are different formal structural linguistic theories to analyze the structure of a sentence. And here I drew you some examples. There are phrase structure grammars, there are dependency grammars, or there are more highly lexicalized grammars. I show you 3 examples. Okay, the first one, constituent grammar. So this kind of grammar can be contributed to a long history, and one contributor is Chomsky, a famous linguist and a politician. So you have a hierarchy of different syntactic phrases to analyze the structure of a sentence. For example, Tim bought a book for Mary. If you're given this sentence, you can see that Tim is a noun phrase. Okay, for Mary is a prepositional phrase, and bought a book for Mary is a verb phrase. Okay, so these phrases are marked with their syntactic category labels, NP, VP, PP, etc., and they embed each other, right? They form a hierarchy. I guess when we were at high schools, we all learned this kind of grammars. And also, next grammar formalism is a link-based grammar. So this is a dependency grammar. So we study the word-to-word correlations in sentences, such as the subject-verb correlation, verb-object correlation, etc. Okay. So another grammar, the third type of grammar, So this is a lexicalized grammar, so-called CCG. So this is a categorical grammar, so which focuses heavily on the syntactic categories that each word carries. For example, okay, if you look at the first line, so NP, noun phrase, N means a noun, and S\NP, this is a lexical category. So it's more complicated than part of speech. What does it mean? It means that this is an intransitive verb, actually. This is an S, sentence category. Okay? / means that it looks to the left for a noun phrase, NP. Okay? If it finds a noun phrase to its left, then it can compose, okay, with the noun phrase and to make an S category. So as a result, it's called CCG, combinatorial categorical grammar. Okay? And the derivation or the compositional process from lexical categories for a sentence is shown in the figure. And you can take a brief look at this figure. So there is a clause, right? So Tim bought a book which Mary likes. So Mary likes is a clause. So likes is a transitive verb. You can look at the lexical category, right? You can look at the lexical category on the top right. So it is a sentence looking for its subject on the left, okay? But this category is bracketed and appended by looking for another noun phrase to its right. So that's the object, right? Someone likes something, okay? So that's the original category. So, but because it's in a clause, so there are some type changes to the word marry, okay? Changing from the subject role to a sort of clause role, and it can compose with the word likes to make a new category. And this new category in turn composes from which, the functional word, into some other categories, like NP / NP. So it's something that modifies a noun phrase on its right, okay? So the composition continues until you find S, a sentence token. And this whole process shows you how the mental process goes on in understanding a sentence. And this process is heavily connected to the semantic understanding process as well, so which is valuable to linguist study and maybe cognitive study. Okay? And then you have a question. Are these necessary for ChatGPT? The answer is no, not really. ChatGPT avoids these processes when modeling a sentence. But what is the value? What is the value of these? Okay. Well, currently, you can see that there are a lot of limitations of ChatGPT. It makes mistakes. So better understanding the cognitive process can potentially help you avoid those mistakes and make models learn more human-like. Okay? So this might potentially be useful for building better models. And these are also of theoretical importance to linguistic study, so they are also valuable. And finally, ChatGPT doesn't do very well on these tasks. Okay? So these tasks require some knowledge which ChatGPT doesn't quite have. Okay? So my student tried them on ChatGPT. The performance was bad. Okay? So there were, after all, things that ChatGPT couldn't do. So next, so a simpler syntactic task is called super tagging. So basically, for example, in the previous slide, you have CCG, and you see a lot of lexical categories. Assigning those lexical categories to sentences are called super tagging. For constituent grammar, if you assign just chunk-level syntactic labels, this is called chunking, is also a type of super tagging. It's shallow parsing on the sequence level without hierarchical structure. Okay. Next, we move on to semantics tasks. So to understand the semantic structure also goes from the word level to the syntactic structure level. On the word level, you have word sense disambiguation. Okay. Maybe the second sentence is more representative. I saw a man. Okay. Saw a saw with a saw. Okay. So the first saw was the past tense for see, right? So the next saw is saw, to cut something into parts, okay, to segment something using a saw. And the third saw was the tool, saw, okay? All right, the fourth was also the tool. So you need to tell the meaning of each word. So this is word sense disambiguation. And the meanings are called a sense. So if you look at your dictionary, right, each dictionary entry is actually a sense, not a word. So you might see 3 different entries for the word saw, because the spellings are the same, but they have different meanings. And there was an important word sense phenomenon called metaphor. Okay, for example, love is a battlefield. So you use a word, okay, to show the meaning of another word in reminiscence. Okay. So metaphor is actually an entry point for modern cognitive linguistic study, because in human cognition, the concepts are quite correlated with each other, right? You use actually physical terms to describe metaphorical terms, right? So this person has a wide heart, okay? So this person is very generous, okay? Okay, so next, on the word level, there are also word-word correlation semantics. I show you a lot of sense correlation examples. For example, synonyms. Words have similar meanings. Antonyms. So words have different meanings. So hypernyms. So the category of one word is another word. Car belongs to vehicle, right? Cat belongs to animal. And there are also meronyms. Okay, so different kinds of correlations between words. And the correlation between word pairs also form a semantic task called analogy. So king is to queen, is like man is to woman, is like a boy is to girl. Okay, this masculine, feminine correlation, right? So if you have a pair of words, you can draw analogy. Okay. Actually, analogy can also be drawn in the sentence level. Okay. I jumped off the building is maybe analogous to the rocket fell to the moon. Okay. You see, in your mind, you can draw analogy between 2 facts. Okay. My heart sank. The ink dropped into water. I don't know if you can draw analogy. In the semantic and cognition level, different people have different understandings, and inter-human agreement is lower. But computational linguistics investigate these tasks, right? They use models to detect whether 2 sentences are in analogy. Now next, at the sentence level, there are also semantics tasks. There's a shallow one called predicate argument structure, which I just mentioned to you. So predicate represent events. Argument represent argument roles that participate in the event. For example, Tim bought a book for $1. So in this case, bought is the predicate. And there are arguments such as the agent, Tim, the patient, book and other argument roles such as the price, etc. Okay, so like semantic role labeling, okay, is a quite general predicate argument structure task, which predict, right, the predicate and the general semantic role such as the agent and the patient to the predicate. So this is a semantic level. But of course, there are more formal like semantic frame tasks, such as frame semantic parsing, which, because of time, I do not go over in this class. So on the next level, if you look at more complex semantic structures, there are graph representations of semantic meanings. So here, I show abstract meaning representation graph. Okay, there are different semantic formalisms. They don't quite always agree with each other. But AMR, abstract meaning representation, is one formalism that is easy to be processed by algorithms. So AMR is a commonly used formalism in computational linguistics. Okay. Next, there are also logic representations of sentences. So this is quite philosophical, right? The study of logic dates back to maybe ancient times, right? So, and if you really understand the meaning of sentences, someone claimed that you have to represent them into logical forms so that you can do inference, logical inference. So, all men will die. So, person A is a man. So you know that person A will die, right? So they kind of logical inference. There are also other forms, at least just a few. For example, lambda calculus. Lambda calculus is one of the very original, very historical type of computation. You know, Turing machine. You know, functional representation. You know, lambda calculus. It's a very, very long-rooted formalism, but it can also be a kind of logical form that can represent sentence meanings. And actually, SQL, you know, the database language, it can also be a semantic representation, and particularly for question sentences. For example, what is the population of China? Okay, so for this sentence can be translated into a SQL query. Okay, and the query can actually be executed in a database table, right? So okay, the semantics between two different sentences. Okay, I give you an example. We saw an example, right? So which is the analogy, two sentences, whether they are similar in meaning in one sense. Paraphrase, whether two sentences have the same meaning is another example. Here in the slide, I show you text entailment. So whether the meaning of sentence entails the meaning of another. Here, we call the first sentence a premise. A premise. For example, Tim went to the riverside for dinner. This could be the premise. And then what can it entail? Another sentence. The second one is called the hypothesis. For example, the riverside is an eating place. Of course, you can infer that this is true from the previous sentence. So the premise entails this hypothesis. But if you say, Tom had lunch, okay? So actually, or Tim had lunch, okay? So we don't know. We cannot infer the hypothesis from the premise. So this is false, no entailment. And if you say Tim did not have dinner, then this hypothesis contradicts the premise, right? So this is not only that we can't tell that this is true, but we can tell this is false. So it's called contradiction. So text entailment investigates the correlation between two sentences, right? So further up one level, at the discourse level, so discourse investigate the correlation between multiple sentences in a larger a text structure. So there are a lot of discourse theories, and I only have time to show you one called rhetorical structure theory. Okay, so there's one passage. So the movie is interesting. Tim wants to watch it. Okay, however, he cannot do it this week because he has a final exam next Monday. So this is a passage. So from the passage, you can segment out a lot of elementary discourse unit. We call it EDU, elementary discourse unit. And I can draw correlations between these units. For example, the first two EDUs, the movie is interesting, and Tim wants to watch it, could be parallel, right? Parallel. And then the next sentence and the next unit and the previous two form a contrast. He wants to watch it, but he could not watch it. Okay, and the first three, okay, and the next one form an explanation. He can't watch it because something. Okay, so discourse analysis in RST, rhetorical structure theory, uses an algorithm to predict these kind of tasks. All right, so a subtask, as I mentioned earlier, okay, is discourse segmentation. You extract elementary discourse unit, okay, and you make use of discourse markers for predicting the discourse relations. Okay. All right. So next, we've seen a lot of computational linguistics tasks. Now we move on to information extraction tasks. So these tasks are quite different from the previous category of tasks. These tasks can be regarded as originating from the late 1990s, okay, when the internet received a lot of attention. People can post news and post discussions over the internet. And at that time, researchers start to look at a task called data mining, or mining useful structured information from a lot of text over the internet. For example, there are a lot of news, and I can know what's happening around the world. How can I know what's happening around the world? I extract event information from news. Okay, so information extraction tasks focus on these issues. So let's look at this overview, okay, IE tasks. From unstructured text, we can extract different kinds of information, including entities, like who, what are mentioned, relations, what facts are mentioned, events, what events are mentioned, sentiments, what opinions are mentioned, okay, all these kind of things, and put them into structured form, put them into structural form. These are information extraction tasks, okay. So first look at entities. So an important task is called named entity recognition. So from news, you want to know what are the persons, what are the locations, what are the organizations that are mentioned, okay? So these are the basic building block for further information extraction. But there are also named entity recognition from other fields, for example, bio-NER. From bioinformatics text, you don't want to extract person, location, organization, but you want to extract what are the chemicals, what are the diseases, what are the drugs, etc. These kind of things. So for different domains, you extract different kinds of entities. So one related task, okay, is called anaphora resolution. You can put anaphora resolution as a computational linguistics task, and you can also put it as an information extraction task. It refers to drawing the correlation between different mentions of the same entity. For example, Tim bought a book and he liked it. Okay, so this he is a pronoun. It refers to Tim, the same person. So, and it is a pronoun that refers to book, etc. So resolving these correlations help you better understand the entities. But sometimes, right, so these anaphras can be zero anaphora, or the pronoun can be omitted. So for example, Tim's book is interesting, and later you say, really like it. Okay, so here the pronoun I is omitted. Okay, and you still need to recover who really liked the book, right? So zero pronoun is not a very often phenomenon in English, but it happens a lot in other languages such as Chinese and Spanish. So it's an important task. So next, so there's a related task called coreference resolution. And the goal is not only to isolate out the correlation between two words in a sentence, but also to extract all the mentions of the same entity and put them together. This is called coreference. So in the first example, right, so we have Tim and he, which mentions the same entity, okay, a person. But we also have the Harry Potter movies and the series, etc., etc. These mentions a film, okay. All right, so those are about entities. If you move on one level, you have relations. Relations are factual knowledge between two entities. For example, Bangkok is the capital of Thailand, right? So, or Bill Gates works at Microsoft, okay? So these are factual knowledge that can be extracted from text. There are person-person relations. There are person, organization, affiliations. There are organization, geolocation, relations, etc. So you extract all those facts from data. So in the next slide, I give you an example. So it contains the correlation between two people, a social relation, and there are like some person working for some organization, and also those geolocations knowledge. So if you're able to extract all those relations, you can put them together to form a knowledge graph. So knowledge graph is a graph structure that assembles all those factual knowledge. Okay, you can see nodes and edges that connect nodes. They represent factual knowledge. Okay. All right, knowledge graph is not completely under study in NLP, but there are related tasks for NLP. For example, entity linking. So when you see maybe a word, maybe a name, maybe bush, right? And you don't know actually which bush this name refers to, but maybe in your knowledge graph there are a lot of different bush and different people. And you try to resolve the ambiguity by linking an entity to one entry in your knowledge graph to resolve like who the person is. So this is called entity linking. And also in biomedical text, you know that different chemicals can be mentioned in a lot of different ways, right? And you normalize the mention into one canonical form. So this is called named entity normalization. Okay. So one task in knowledge graph that is also studied in NLP is called link prediction or knowledge graph completion. So this refers to the fact that no knowledge graph is complete. No knowledge graph contains everything, every knowledge you know. So sometimes, given some knowledge, people can refer facts. For example, if you know John is a singer, John is from Rome, Rome is in Italy, then what do you know? You know that there is a singer in Italy, at least, right? Italy has a singer. So this kind of inference tasks are called knowledge graph completion. Okay, so those are about relations, right? Entities, relations. So next, events. A lot of useful tasks about events. For example, if a news mentioned Trump visited Tokyo, then you know that some event happened. And the type of event can be diplomatic visit, and there are argument roles such as the visitor and the target, right? So these event extraction tasks are quite related, as you can see, to predicate argument structures. Next, so also related to events, people study other useful tasks. For example, there are social media, such as tweet. There are a lot of tweets every day, right? They mention things, observations around us. Sometimes people tweet about events quicker than the news agency. For example, I can tweet, oh, the earth is shaking. I can tweet, I was lying on sofa, but suddenly the cup fell off the desk. So these kind of things are earlier, like first story clues, okay? So if you can extract or infer events from such tweets, then this task is called first story detection. It's quite useful, right? It can help you organize rescue efforts, right? Before a news agency know that earthquake happens, right? So if there are also some social events that need attention, then maybe you can detect them from tweets. Also, facts, text from the internet can be true or false, right? So the news trustworthiness or event factuality prediction is another interesting task. Right? Some people working in NLP focus on these. Can I trust the news? If you ask ChatGPT, right, what's the population of the US? And ChatGPT tells you an answer. Is it true? Right? Can you verify the fact? Right, if you ask ChatGPT how many times a certain basketball player, how many matches a certain basketball player has played, right? And ChatGPT gives you a number. How can you verify this is right or wrong? Right? So this is about factuality. Also, the temporal relation between events are also interesting. How do I know which event happened earlier than another event? Okay, or the causality of events. This is very useful for finance. Okay, does this event cause another event? You need to take financial actions, right? So the iron price increased. Okay, and then what kind of companies' price will increase or decrease? So the causal correlation between things. So next. So events, they also have coreference, correlations. For example, I interviewed Mary yesterday. It went smooth. So this it doesn't refer to Mary or I, right? It refers to the interview events. And event coreference can also be omitted. For example, I like World Cup. And Tom too. Okay. In the second sentence, likes the World Cup is omitted, right? You should be able to detect that. Okay, final task concerning events. There is something called script learning. This is a structural information extraction about events. So for example, if you visit a restaurant, it's one event, right? But it contains a lot of sub-events that are partially temporarily ordered. You should enter the restaurant, you should maybe sit down, you should order food, you should eat food, right? And then you should pay your bill. You should leave the restaurant, okay? There are a lot of sub-events. They are temporarily, partially correlated. So script learning is the automatic extraction from script from text. It's quite useful for gaining world knowledge. As a result, script learning can also be treated as a computational linguistics task. concerning semantic frames, so which I didn't introduce to you earlier. All right, those are about events. So the next is about the sentiment. Okay. Sentiment extracts opinions or the attitude or the emotions. Okay. But sentiment is not exactly emotion. Sentiment is the polarity. For example, I like the song. I have a positive sentiment towards the song. Right? I don't like the game. I have a negative sentiment toward the game. There are different sentiment analysis tasks. A simple task just classifies a given text into positive or negative. Oh, the movie is great, positive. Okay, the basketball player is boring, maybe, negative sentiment. But there are also more fine-grained sentiment tasks, such as targeted sentiment. So say, this camera is light, okay? But the resolution is low. So this piece of text is a mixed sentiment. So you have to extract. Okay, the positive sentiment is on being light, right? And the negative sentiment is about the resolution. Resolution is low. Okay, so this is a fine-grained task. But there are also like even more fine-grained sentiment tasks, such as Mary scolded Tim because he lost his watch, for example. There are like opinion holder Mary, okay, opinion target Tim, and opinion expression scolded, and an opinion reason he lost the watch, etc. It's a very fine-grained sentiment extraction task. All of them are very useful. I take stock analysis, for example. If you want to know, okay, which companies will have increased price, for example, right? So what do? You look at all the tweets concerning the product, the management team, about the user, okay, and you extract the sentiment from everyone, and you can predict whether the stock price will increase. Okay. Okay, next are correlated tasks to sentiment analysis. For example, sarcasm. This is an interesting task. GPT doesn't do this quite well. I really like it. Okay. Do I really like it or do I really hate it? Okay. Great. Okay. Did I do some bad things or did I do some good things? It depends, right? You have to understand the context to understand sarcasm. There's emotion detection, as I mentioned to you earlier. So when I say something, what's the emotion behind the word, right? Is it frustration? Is it like excitement? So emotion have different coordinations. It's a very complex thing. There are psychological studies of emotions. There are computational studies of emotions, but NLP covers emotion study, which is an interesting branch. So one more related task is stance and argumentation. What is stance? Stance is your opinion towards something, but it's not necessarily sentimental. Okay. For example, I support nuclear energy. Why? Oh, because it's generally clean, and it's cheap, etc. Okay, I have a stance. I support it, and then I give my argument towards the stance. Okay, but I can also stand against it. For example, it's dangerous. So if you have an earthquake, it might cause severe pollution, etc. So stance and argumentation, you analyze these kind of structures. Okay, that's all I wanted to say about information extraction. There are more tasks, but if you know this big picture, You can easily read papers about them. Next are text generation tasks. This is, again, a very broad stroke area. So, for example, you have realization, which is to generate a sentence that represents a given meaning. This is called realization. It's from computational linguistics study. There are also data to text generation. For example, if I give you a table, for example, the stock price behavior or the result of a match, you generate a sentence to describe it. So data to text generation. There are summarization. You're given a long text. Okay, Wall Street Journal articles can have millions of words. Okay, up to 1 million words. How can you extract a small part that describes the original passage? Summarization. Machine translation. Okay, so the name is self-explanatory, right? There's grammar error correction, where you're given a grammatically incorrect sentence and the algorithm corrects the mistakes. There is question answering, okay? So which ChatGPT is quite good at, right? So you're given a question and the algorithms give you an answer. Question answering can also have different types. So for example, there's reading comprehension. You give a passage and you give a question, and the algorithm reads the passage to answer the question. This is a simpler form of QA. There's also community QA. For example, you have a website, Quora or Baidu Answers, right? There are a lot of questions and answer pairs, and then the user gives you a new question. You help her find a relevant answer to the question. So this is called community QA. Of course, what ChatGPT does is open QA, open-ended. You just ask a free question, and the system gives you an answer. Okay. There are also dialogue systems. You already saw, you already had a dialogue with GPT, but there are also task-oriented dialogue systems. The system will just help you achieve a task. For example, I want to buy something. Okay. Can you show me some white tables? Okay, here are white tables. What do you like? How about the second one? Are there things that are similar to it? Okay, here are things that are similar to it. They look too expensive. Are there cheaper ones? Oh, here they are. So this is an interactive dialogue for you to achieve some goal, right? Like purchasing something. So these are task-oriented dialogues. Okay. So those are text generation tasks. Now finally, we have other applications related to NLP. So the first one is information retrieval. So this is not a pure NLP task. Okay, IR by itself belongs to data mining. Okay, so that's another field. But there is an overlap between IR and NLP because for information retrieval, a large body of information is represented in text, of course. So NLP is related to information retrieval. Recommendation systems. It also belongs to IR and knowledge mining. Okay, but if the thing have text description, then you do recommendation. You have to use NLP technology. So recommendation is also covered partly in NLP. Finally, text mining. So this is also part of data mining, but the target is text. How do you do analytics over text? For example, stock price prediction based on news. That's a typical text mining task. Or you can help a business better organize itself by analyzing the employee behavior, whether they're malicious insiders, malicious emails. So these are all text mining tasks. Okay. Okay, I've spent an hour or so talking about what are the tasks in NLP. So next, I will tell you why do you want to learn NLP from a machine learning perspective. Okay. So So what is machine learning perspective? What is not a machine learning perspective? So one perspective to learn NLP is from a linguistic or task-driven perspective. So I show you a task, and then I show you how to solve the task. Okay. Next class, I show you another task. I show you how to solve that task. That could be one way to organize an NLP class. But there is a limitation of that task because the underlying methods are common across a range of tasks. So machine learning is the fundamental technique that supports different tasks. Okay? As a result, if you learn the machine learning technology, you can easily pick up the method behind different tasks. So that's one reason, right? You organize the materials into machine learning. Secondly, tasks, they evolve, okay? As time evolves, people realize there are new tasks that are necessary or that can be solved. There are old tasks that are no longer irrelevant. I can tell you a lot of tasks, such as prepositional phrase attachment. I eat pizza with fork. I eat pizza with meat, the two sentences, okay? This with something attached to different words. Eat with fork, right? Pizza with meat. See? The prepositional phrase that they attach to different locations. Why is this task irrelevant now? Because people have developed very accurate parsers. They can analyze the whole structure of a sentence, so they don't need to study particular prepositional phrase anymore, right? Tasks, they evolve, but underlying machine learning technologies, they support new tasks. The third reason, maybe a very relevant reason right now. The third reason is that as deep neural networks go deeper and deeper, one network can solve a lot of different tasks, okay? So more and more people turn attention to general models rather than task-specific models. That's a great reason why you want to learn NLP from a machine learning perspective, and a great reason to support my organization of the class, okay? Now, if you look at the machine learning perspective, you'll see a lot of structures. For example, the tasks, they can be classified into classification tasks, structured prediction tasks, regression tasks. What are classification tasks? So you're given something. You want to tell what category this something belongs to, positive or negative. Political news or finance news or technology news, right? Spam email or non-spam email. So this is called classification task. The output is one of the few classes, right? So structured prediction tasks. You're given a text. You want to know the structure, the syntactic structure or the semantic structure. These are called structured prediction tasks, okay? Actually, text generation is another structured prediction task because the sentence is a structure. It's not one of the isolated classes. Regression tasks. For example, stock prediction, you predict the price. This is a regression task where the output is a number rather than a discrete label. There are other ways to classify machine learning method. For example, unsupervised learning. You don't have output labels, you just have raw data. How can you learn how to perform a task? Unsupervised learning. Supervised learning, you have the input and output pair, you learn a model. Self-supervised learning, you only have the input, you don't have output, but you want to learn a representation model for the input. Distant supervised method, you have sort of a labeled data for one task, but you want to learn another task, right? Distant supervision. Learn one task from another task, distant supervision, okay? So the class will be organized according to the nature of the machine learning problem. Okay. And I mentioned to you in the beginning that we will spend 16 weeks. The next 15 weeks will be organized into three main parts. The first part covers chapters 2 to 6. They are the fundamentals. You learn the basic thinking behind modeling. You learn some basic probabilistic modeling ideas. You learn some basic vector space models, okay? Both supervised and unsupervised, but you also learn some information theory, such as entropy, mutual information, etc. So all these are the fundamental building blocks of statistical models, probabilistic models, non-probabilistic models, so weeks 2 to 6. And then the next few weeks will cover structured prediction tasks. These are very unique. For example, you will learn sequence labeling methods. How do you label a sequence of words? How do you predict a tree? Okay, tree structure prediction. If you do parsing, semantic parsing, information extraction, you need this structured method. The third part, we will just focus on deep neural networks. You will extend what you learn from the first part, the single-layer perceptron to multi-layer perceptron. That's a neural network. You will learn different neural networks, transformer, for example. And you will learn how to train these neural networks and pre-training. GPT, BERT, you will learn them, okay? And by the end of week 16, you will gain enough knowledge to read new papers and to embark on your research in the NLP field, okay? So I think that's the end for this week. See you next week. Okay.